These are my slides if you want to look at them on a computing device. Sometimes the code, this is, unfortunately, I have to apologize that early in the morning I'm going to be doing a very technical talk. But there's a lot of code on these slides, and you may want to like look at it on your computer. So while I take a quick photo for my mom, you can load up that URL before I take it off the screen. She's always really confused. She's like, where are you going in the world again, and why are you doing it? I don't understand. Okay, so this is a talk about Rust. And as you know, Rust is not Ruby. And this is a Ruby conference. So why would I talk about Rust at a Ruby conference? So I guess first of all, I should preface this with what Rust is. So Rust is a programming language written by Mozilla. And it is currently pre-1.0, like 1.0 is going to happen this year. And I happened to get involved with Rust about a year ago, a little over a year ago now, almost a year and a half. Wow, time flies. Because I really like programming languages, and I like learning new programming languages and like experimenting with them and comparing and contrasting things. While I love Ruby, it's definitely not the first language that I used. And so when I learn new languages, I like to maximize my amount of new knowledge I'm going to know. So I try to learn things that are very, very different from what I learned previously. So for example, I used to be a PHP programmer, and then I tried learning some Haskell, because it's like very, very different, so you learn a whole lot. So when I had heard about Rust, I saw the pitch for Rust, which is basically a language that's strongly statically typed, has really good concurrency support, and is very, very fast. And I went, wow, that's the exact opposite of Ruby. I'm going to learn a lot by learning Rust. So I want to share what I know about Rust with all of you, but first, I guess, before I get into like the code and the more details about Rust and what it's like and what it is, I want to explain to you why I'm bothering to tell you all this stuff. So this is something that we all say about Ruby all the time. So people say Ruby is really freaking slow, right? Like yesterday we had multiple comments about Ruby being slow, and Ruby is slow, but that's not the point, right? We don't use Ruby because of speed. And one of the when someone says, oh, I would never use Ruby because it's slow, you come back to them and you say, yeah, but I don't care because Ruby has really great support for FFI and C, so I'll just drop into C whenever I need performance. But then you just don't ever do that, right? I actually did. My very first Rails app included a C extension, so I have actually done this, but I don't know if it was actually that much faster. So this is hello world in Ruby, puts hello world, and that runs in 0.037 seconds, basically, on my machine when I ran it a bunch of times. The same hello world in Rust, which I'm going to talk about a little bit later. I'll show you exactly what this code is like. But the hello world for Rust is 0.004 seconds. So you're talking about, 37 to 4, so 10 times faster for hello world. And there's a lot of reasons for this, but a 10x speed up would be really nice for a number of different reasons with things that we're doing. One of the things that we're all sort of being angsty about as a Ruby community is the fact that we have been building Rails apps for a couple of years, and now we're all cursing our past selves for all the bad decisions that we've made. I actually have the very first Rails app I ever wrote. It was for my startup that I had a very long time ago. We did not manage to succeed, so this app is no longer in production, but I have it in a zip file, and I'm just waiting. I think I'm going to give it about another 6 months or a year before I write a blog post at look how terrible my first Rails app was, because I think it's really interesting to see how far you can come in 6 or 7 years. So a lot of people have a lot of really mature Rails applications. They're very, very large, they're very hard to maintain, and they're very slow. And so what people have been doing, one of the strategies that people have been doing to deal with this issue with Rails applications is to extract services, right? That's like the hot thing right now is like service-oriented architecture, a million little tiny services. And this is how people are breaking up these big monorails, right? So how do you eat an elephant one bite at a time? How do you eat a monorail one bite at a time? Through these kinds of services. And so one of the things that I see as a possibility for Rust and why I might be interested for Rubyists is that if you need to, my monorail is big and giant and slow, so I'm going to extract a particular service that does some kind of processing, you can write that in a different language, and expose it over, say, HTTP, and your Rails app thinks it's talking to, it doesn't matter what kind of code it's running, right? So I see a sort of near-term future for Rust for Rails applications where we write back-end services in a sort of SOA style in Rust when we need the performance. So you sort of like build a Rails app all in Ruby, and you say, oh wait, I am doing image manipulation, and image magic is terrible and hard to install and horrible, so I'm just going to write that in Rust instead, and those kinds of things. The other reason that I want to tell you about Rust is because I'm not the only Ruby person that is interested in Rust. I managed to convince Yehuda of Rust's utility, and so Yehuda Katz has also been very heavily developing Rust code. Tilda is actually being contracted by Mozilla right now to basically write bundler for Rust. So like Rust will have a bundler for 1.0, which is going to be really nice. And you know, learning from all the mistakes, my roommate is the current maintainer of Bundler, so it's kind of funny when I tell him that, he sort of cries a little inside. And I'm like, no, all the lessons we learned from writing Bundler are going to be fixed in this next time. And Tony Arcieri is also another like big name Rubyist who's been heavily involved in Rust because Tony's the guy who writes Celluloid and a lot of the concurrency stuff, so he's very interested in the concurrency aspects of Rust. And there's a whole bunch of other people too that are coming over, but whenever you find out something cool, you want to bring all your friends with you, right? So like I would like to share this cool thing with you, so hopefully you will also not just code in Ruby with me, but code in Rust with me. Basically, I couldn't find the tweet because Twitter's search is terrible, but Yehuda's perspective on Rust basically boils down to, and if you take nothing away from this talk, this is like the summary, essentially. Rust gives you the safety and convenience of Ruby with all the speed of native code. So for example, in Ruby, we don't have to worry about memory management, right? This is why all our Rails apps take up all our RAM and why we need to buy new servers that are bigger, like we talked about yesterday, because we don't care about memory, it just happens, right? And the reason that we don't care is because it's convenient and we like not caring. But Rust allows you to have that same sort of like care while not using as much memory and you're causing all those problems and bugs that happen. So yeah. The other thing I want to say sort of meta before we get into it is this, Rust versus Go. So people keep bringing this up, and it's unfortunate, I think, because I don't actually think that Rust and Go are comparable, and it's sort of the official position of the Rust team that Rust and Go are not really competing in any way. But this is the first question that everyone asks me when I say, oh yeah, I do a lot of Rust programming. And they go, oh really, what about Go? The issue is basically Go is like a lower level Ruby or Python, and Rust is like a higher level C or C++. And this does mean there is a tiny amount of overlap, but there are programs that Rust is like specifically good for that Go is bad at, and there's a lot of things that Go is really wonderful at that Rust is really bad at. So I don't think that it's really accurate. They're four sort of different kinds of things. One of the big problems is that the Go team initially misjudged who would like Go. So Rob Pike, one of the inventors of Go, wrote this blog post where he basically said, I was really surprised because I was writing Go to like steal away C++ people, but actually I just stole all the Python people instead. And okay, sure, but like that's really confusing. And so Go initially advertised itself as being very similar to Rust, and I think this is the root of the confusion. And the Go team has been sort of modifying their marketing to like stop talking about systems programming because Go is not really good for what most people refer to as systems programming, but some other people do. Words are really hard, right? Like I said yesterday, MVC, no one knows what MVC actually means. Every MVC implementation is totally different. So it's sort of the same with systems programming. Anyway, that's the other thing I just want to say, and meta sort of things. So there's a couple different sections of this talk that I actually want to getting into the actual details instead of just meta stuff. The first one is I want to talk a little bit about low-level programming because that's sort of one of the things that I really enjoy about Rust is that it's so much more low-level than Ruby. But not everyone has the sort of, I learned low-level programming in college, largely. I mean, I programmed in C before college, but my C code was terrible and full of bugs and crashes. So I really learned this stuff in college, but I know a lot of people did not go to college or their college didn't make them take those classes or whatever. So I want to talk a little bit about low-level stuff. And then I want to show you a whole bunch of Rust code and some interesting features, what it looks like, and like some stuff about that. And then talk about production and deploying Rust. And then this slide is not appearing for some reason. Oh, learning more. Apparently I have an extra div in here that's causing an extra thing. And then like where to go to learn more after the talk. Okay, so learning the low level. Again, it's 10 a.m. the second day of the conference. I appreciate you all being here. Thank you. We were all at the bar relatively late last night. It's always very hard to be the first speaker on the second day of a conference. But I apologize. We're going to start talking about pointers. I didn't write the schedule, not my fault. So let's talk about pointers. Actually, I'd just be curious. Who here has done low-level like C or C++ programming before and knows about pointer stuff? Cool. This will be a review for you. You can all sort of go to sleep, kind of. No, I just more want to talk about this to sort of show the different kinds of concerns in Rust that matter to Rust programmers as opposed to Ruby programmers. The details are not actually, they're important, but I don't expect you to there will be no tests. I will not be mad if you don't remember things about pointers that I explain right now. So the first thing that I want to talk about, and this is the thing that I think is one of the most significant things that I learned, again, from going from Ruby to Rust, is the difference between stack versus heap memory. And this is something that, as a Rubyist, you don't even think about at all, ever, whatsoever, but matters a lot in Rust. And so it's one of the things I think is most productive. So before I get into the code, I want to briefly cover stack versus heap stuff, because it matters, and it's a refresher, since a lot of you already know this kind of thing. So stack memory is what happens when you, in a language like C, when you declare a variable, it's by default on the stack. And the stack memory is managed by the CPU. So the CPU handles when you context switch, moving stack stuff and all these other things. Stack memory is sort of function local. A variable goes out of scope at the end of the function, and then it's gone, right? That memory is not valid anymore. And so that's what happens when it's on the stack. The nice thing about stack memory is that it is super, super fast. There's a variety of things that sort of play into why this is fast, but it's really, really, really quick to allocate memory on the stack. One of the downsides of stack memory, though, is that you only have a certain amount of it. So you can't always stack allocate everything. And in order to stack allocate things, you need to know how big they are in memory first, and there's a whole bunch of details. So it would seem okay, it's super fast. Why would you ever not use stack memory? That's one of the big downsides. Heap memory is what happens when you call a function like malloc instead. So instead of you declaring a variable and that handles it that way, you call malloc, you get a bunch of memory on the heap. The heap memory is managed by someone. So the language and the compiler and the CPU take care of the stack memory, but in heap memory is either managed by you if you're using malloc and free in that sort of old school C or C++ way, or if you're in Ruby, it's managed by Ruby itself and the Ruby runtime. So someone has to keep track of how much memory you've allocated and when to throw it away. In this way, it's sort of global. If you declare some memory on the stack, it's valid even after the function is gone. It's valid until you call free, because you or Ruby is allocating and deallocating this memory. And so it's much, much slower, because you have to actually call to the operating system and go into the kernel and do all this crap. And then also it's hard because it's global, it's much more difficult to reason about, right? So if you have a global variable and you mutate it from everywhere, you're going to have a bad time. Right? But this is sort of what happens with heap memory, because you have to keep track of what stuff is pointing to what stuff and all these other kinds of things. So that's the downside of heap memory, is that it's much, much slower. But the nice thing about it is that you have a whole ton of it, and you can do all sorts of other things. Also, I would say this too. So in Ruby, everything is heap allocated, basically. A little asterisk if anyone's an MRI committer here, that's not strictly true, but effectively everything is heap allocated in Ruby. And this is why our applications take up so much memory, because we're doing all these things globally, and everything involves allocation, et cetera. But this is why you don't sort of need to think about memory in Ruby, is because it's all heap allocated, and Ruby manages the safety aspects for you. So you don't have to think about it. But that means we lose all of the benefits of stuff like speed. So benchmarks. This is a bunch of Rust code, and I haven't actually explained what Rust syntax looks like to you yet. Can you see that? How good is that? Okay, cool. Sometimes it's hard with the light and the highlighting gets a little wonky. So anyway, this is some Rust code. It doesn't really matter the specific details, but basically Rust actually has benchmarking built into the language. So you can write a function and say this is a benchmark test. And so in the first test, I allocate the number 5 on the stack, and on the second test, I allocate the number 5 on the heap. And so if you compile this, first of all, you get a warning, which is really amusing, about main is never used because it's a test file, so whatever. There's ways you would get around that. I don't know, this is not important. But you get some warnings, but when you run these benchmarks, it takes about 243 nanoseconds per iteration for the heap allocation, and it takes about 77 nanoseconds per iteration for the stack allocation. So again, this is sort of demonstrating how much faster it is to allocate things on the stack than the heap. That's what, a 3-time difference, basically. Same sort of thing as before, like a 3-time speedup would be amazing, right? Like if you could serve 3 times more requests per second, you could buy smaller servers, you could, do more requests, like all sorts of stuff. So sort of just like generally, demonstrating the difference, not just take my word for it, the stack is faster, there's some empiric data. But in Ruby, everything is heap allocated, as I mentioned. In Rust, wow, this works different on my laptop than on this one. I'm sorry, the words are being cut off. So in Rust, we prefer stack memory because it's faster and easier to reason about, but we also have safe heap memory, but in a different mechanism than Ruby uses, which is like everything is managed by the runtime. In this case, heap memory is still managed by the programmer, but Rust gives you tools to help you do it, so it's easier. So what do I mean by memory safety? This is sort of the core goal of Rust, is like, can you do manual-ish memory management while still retaining safety? So now we're going to talk about some C code. So the reason that other previous low-level languages cause lots of problems and headaches for their programmers is that they basically let you do whatever you want, and humans are very, very fallible, right? Like, I probably make hundreds of mistakes every day, right? I'm constantly going, like, I always joke that I think get blame just returns your username, right? Like, whoever is currently running it, it says that. The number, every time I've been like, man, what idiot wrote that code? I'm gonna look and get blame, and I'm gonna ream them, tell them it's so wrong, blah, blah, blah. And then it's like Steve Klabnik. I'm like, ugh. So this is the kind of things that happens in C. So I don't expect you all to know C, but basically we allocate an array of characters, and then we copy the string hello world into that array of characters, and we print it out. And this works. But this is totally fine. There's no problem with this code. But let's do a little bit of refactoring on it. It's sort of weird to allocate this array and then copy the memory into it. Maybe we want to do this multiple times or something. So let's extract a method. So instead, I'm going to make a pointer to a string and call makeString, and then in the makeString function, I extract that code where it gives you a character array, and then copies the string into it, and then returns it, right? So this is sort of like a factory or like a method extraction. We do this in Ruby all the time, but this code is horribly broken. And what's funny about it is it's broken even in a way that if you know it's broken, you can still be wrong about how it's broken. So when I was writing this example, I went, this memory is totally invalid. This code is going to segfault. Turns out on GCC, this just prints nothing. And my understanding of C's semantics says this should segfault, but it doesn't. So even though I'm Mr. Presenter and I started programming in C when I was 8 years old. I have a lot of experience with C, and I still get this wrong. So now it's true that GCC will print out a warning that says, hey, you're probably doing something stupid in this case. So a lot of C and C++ compilers have developed lints to tell you when something is probably wrong. But I've seen some more complicated examples in C++ that I didn't want to go into all the details, where you can actually compile with GCC with all the warnings on and say warnings cause errors and whatever, and it will still compile and then segfault. So there's all kinds of these issues with memory. And the reason why this fails, we were talking about the stack versus the heap earlier. So this actually allocates the character array on the stack, which is valid memory, copies the hello world into it, but when we return the reference to that stack memory, it goes out of scope, right? And then that S variable is invalid. So in Ruby, it would be allocated on the heap, so we'd be passing that value back, but since it's a stack memory, it goes out and it's gone. So that's where the bug is. But this is just patterns that we use every day in Ruby just totally fall down in lower level languages. You know about the Pwn to Own competition? So every, I think, year, they have this competition called Pwn to Own, and basically all the major browser manufacturers put up prizes, and they say, if you can hack our browsers, you get $20,000 or 5 iPads or I don't know, stuff. And so every single time, every single browser always has terrible security vulnerabilities. Like, security researchers show up and they're like, oh, yep, 6 bugs, like, found them all. And so in the last pwn to own, the one that just happened like a month or 2 ago, I want to say, relatively recently, Firefox had 4 very serious vulnerabilities that all involved, you load up this website and I can run arbitrary code on your computer, which is bad. And all of those 4 bugs were all related to this memory safety issue I just showed you. So there's like invalid memory that gets overridden and a buffer overflow happens, and then like, whoops, you're screwed, all this kind of stuff. All 4 of those bugs would have been impossible if Firefox had been written in Rust, due to Rust's stronger guarantees around safety. So this is what motivates Rust, and this is why Mozilla is working on Rust, and this is why I'm excited about Rust, is because you can actually make entire classes of bugs just straight up go away. So like buffer overflows are impossible in Rust code. Use after free is impossible in Rust code. And that's really, really cool and awesome. So that's sort of why I care about this stuff. And this is also why Mozilla cares about this stuff. So, okay, I've spent the first, like, what, 20 minutes of this talk not even talking about what Rust code actually looks like. Sorry. So let's get into it. Let's check out some actual code. This is the example that's on the Rust homepage, and it has a whole bunch of interesting stuff in it. So the very first thing is like function main. So in Rust we use fn because typing function everywhere sucks. And you just put down main, and you don't need to actually take any arguments. If you're familiar with C or C++, you can take in arguments from the operating system. You can, if you're not using them, you can leave them off. In general, Rust feels very similar to curly brace kind of languages, and it wanted to be vaguely familiar. But there's some weird kind of Ruby-ish stuff in here too. And one of the things that attracted me to Rust actually is that a lot of the syntax and naming conventions are very similar to Rust and Ruby. So you don't use camel case, you use underscores, constants are capitalized with the first letter as opposed to everything else, like all these kind of things. So anyway, in this case, we make 2 arrays. One is nums and one is nom, so numbers and names. And so number 1 and 2, and the names Steve, Matt, Aaron, and David. And then you create this variable odds. Now, one thing you may notice, it says let mute odds instead of let nums. So by default, variables are immutable in Rust. There is actually a very, very heated and complicated debate where some people want to change this. But right now, everything is immutable by default. And this is because in like functional stuff and all sorts of other reasons, only using mutability when you need it reduces bugs. So in this case, we make odds, we take the nums, the numbers, and we make an iterator out of it. So we say, please give me an iterator that will iterate over this array. And then we call map, which you know from Ruby, right? Map calls a function on every single element of the array and returns a new array. And the syntax is very similar. You have the pipes with the argument name in the middle. So this takes a reference to a value called x, and then it takes x times 2 minus 1. So that will turn any number into an odd number, basically. So then we do a for loop. So there's no like low level like for I equals 0, I is less than whatever, I plus plus, because those are terrible. We don't do those anymore. Rust just lets you say for num in odds, and that will iterate over every element in the array. And then spawn is a library function that spins up a brand new task. So this is spinning up threads for every element in the array. And then proc is like proc in Ruby, and then it makes a procedure. So this is a lambda. The difference between the lambda you pass into the map and the lambda you pass into spawn is a technical distinction that I don't want to get into, but there are multiple kinds of lambda, just like in Ruby there are multiple kinds of lambdas. And basically we print out, this person says hello from a lightweight thread. This sort of substitution syntax, the curly :s curly, says print a string. In other systems languages, you use like %d or %s, or in Ruby you can also do that if you use like string format functions. But this is the Python way of doing it, and there's a number of reasons that this way is better. It's better for internationalization. You could actually you could name the arguments and pass in named arguments and a whole bunch of other stuff. So it's a little weird, but you get used to it, and it's much better once you do stuff. And then just basically just accesses the element of the array, right? So the number in the names array. And so this will print out a bunch of stuff. So this example is not particularly interesting. It just shows you a whole bunch of random stuff. So I just wanted to kind of you can check it out and get a feel for it. Now I want to talk about more this is another example that has a couple of other really interesting things in it. So this does an integer calculator. So you take a string with like pluses and minuses and multiplies and divides. And what it does is it starts off at 0. And then if you say like plus, 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 it prints out 3. Plus, minus, plus, it prints out 2. Plus, 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 divide gives you 2, if my math is right. Basic integer addition is so hard. So in this case, though, the interesting thing I wanted to show you is the match statement. So what this does is it takes the program, it loops through the characters with a for loop, and then it calls match on each one of them. And match is sort of like a super souped up case statement. So in Ruby, we have case statements, and you can say, like, here's this variable. If it's this, do this. If it's this, do that. If it's this, do this, right? And it's way nicer than writing if, ELS if, ELS if, ELS if, and like all those kind of things, right? But what's cool about Rust's matching is that it actually takes a pattern on the left-hand side and then uses the hash rocket as what happens on the right-hand side. So if it's a plus, we add 1 to our accumulator. If it's a minus, we minus 1 to the accumulator. If it's an asterisk, we multiply and divide. But the last line is the one that's most interesting to me. And so in Rust, it actually knows what type the token is. And so it says, oh, a token is a char type. So if you, it makes you handle every single case. So if I had left off this last line, Rust would actually fail at compile time and say, hey, you're only handling 4 out of the infinite possible character, not infinite, but sorry, Unicode, maybe infinite, it's complicated, early in the morning. There's a lot more characters than these 4, right? So Rust will actually say, hey, you didn't handle those other cases, so you have to do it before I will let you compile the program. And so this is really, really neat. And so the underscore, just like in Ruby, basically just says, I'm going to throw away whatever this is. I don't care. It's everything else. So this is sort of like the final else case. In this case, we just don't do anything. We're just ignoring invalid input. And then we run it, and we print out the value, right? So, but this match statement is super neat. And another thing that's like basically stolen from like Haskell or OCaml if you've ever done like functional languages. And once you have it, you miss it in other languages. Okay, let's talk about writing your own functions. So this is a very simple program that has a main function that just gives it a variable x is equal to 5, and then it has a function called +1 that adds 1 to the number. So here is interesting. So we allocate this 5 on the stack, and then there's this ampersand x. And what the ampersand does is it says, hey, please send a reference to this. So it's a pointer to that value that's actually passed into the +1 function. And if you see fn +1 takes an x of type ampersand int, which means a reference to an integer, and it returns an integer. So main doesn't have a return type in Rust. So this is the syntax for having functions with return types. You can leave them off if you're not returning anything. But the arrow is like, I don't know, it's nice syntax, right? It's pointing towards, I joke I have this big arrow tattoo on my arm, so I always laugh when I'm like pointing at like screens. It works really well. But the asterisk x, because this is a reference to an x, if we said x +1, it would go, hey, you can't add a pointer to a number. That doesn't make any sense. So the x says dereference the pointer and give me the value that it's pointing at. So in this case, that like unwraps the pointer aspect and gives you, 6, and it prints it out. So this is just like very simple passing things around. Now, if we wanted to allocate this on the heap, it would be almost the exact same code. The difference is that let x equals box 5. And if you've seen Rust previously, this used to be a tilde character, but we changed it to box for a number of reasons that I don't want to get into at the moment. We can talk about it later if you want. But basically, box is a term, if you ever use Java, right, they talk about boxed versus unboxed values. So integers are not boxed, but all characters are boxed. Basically, it just means it's allocated on the heap instead of the stack. And so what's cool is type inference lets you do this really easily. So we actually have been leaving a lot of types off except for these function signatures, and Rust actually does full Hindley-Milner type inference. So we didn't actually need to change anything in our code except for the box, and it sort of figures out all of the rest of the stuff and makes sure that we're still doing the right thing. We don't have to be super verbose about it. This is something that's different. So I did a lot of statically typed programming before I came to Ruby. So I actually programmed in Perl first, and then Ruby whenever, Ruby is basically just like Perl, but better in every way. And so, like, a lot of people are used to the Java-style static typing, where you end up putting types everywhere and it feels really gross and you like got to do all this crap. But like the more modern statically typed languages do so much type inference for you that it can feel like you're programming in a dynamically typed language, even though it's automatically checking all these cases for you. It's very, very rare that you need to declare the type of a variable. So that's also one of the cool things about if you haven't done statically typed programming in a while, or if you haven't done it before, more modern statically typed languages feel a lot different than older ones do. Here's another concurrency example. So in this case, Rust has channels. So if you want to communicate between tasks, the way that you do it is you create a channel, and you can send information down the channel to the other task. Again, tasks being like a thread, basically. So in this example, we make a channel and a port. So these are two variables. You can think of them as like one end of each of the telephone cord, right? And this also shows you that like Rust has what's called desugaring assignment. So channel actually returns like two things, and you can assign them in one let statement, basically. Ruby does this as well, if you've ever seen this in Ruby. I don't know, it's not a super common pattern, but Ruby does it. So we basically spin up this task, and we say let result equals 5, and then we send a result, we send that 5 down the pipe. And so this thread spins up, it makes a 5, it sends it back to us, we receive it back in the main function, and then print it out. Pretty basic. This is how stuff communicates. Yes? So the question is, why is channel not on the heap and then accessed inside the proc? That's a good question. I believe that both the channel and the port are actually heap allocated, and that is inferred from the types. And so what happens is when you use it inside the proc, it sends the pointer over, basically. Little bit hazy on some of the details there, but I'm 99% sure it actually is allocated on the heap. Okay. Here's a slightly more complicated example where we actually make a boxed 5, and then we pass in explicitly. So this is the other way that you can pass in variables to another task, is if you just use them. So Rust static analysis basically says, hey, you're using X inside of this lambda that we passed to this other task, so it just takes it from main. So what happens here is we make this variable X, and then we use it inside of the procedure, and so that's totally valid, and now it prints out 5 plus the value of X, which is 5, and so this will print out 10. Now, this is a very common kind of thing in other languages where you can send data over to other tasks. And in Ruby, you can do this too, right? So because procs capture the environment, if you do this in Ruby with thread.new, you could reference variables from outside the scope. But the issue here is that if you do this, now you have two different threads accessing the same variable at the same time, right? And we all know that's bad. And that causes bugs, and it's terrible. And this is really hard in Ruby, and it's one of the reasons why Ruby concurrency is so awkward, is because we have to deal with this kind of issue. So what's really, really cool about Rust is if I try to use X afterward, so this is the same code, but I have this, the result of X plus equals 1 after this procedure happens. This would be valid Ruby code if we translated it over, and it would cause a data erase condition. So sometimes this would print out 10, sometimes this would print out 11. This actually gives you a compiler error in Rust. Yes. There's also that. I'm getting there too. Two things at once. We don't have that much time, but good call. So there's two things. The first one is Rust says, hey, wait a minute, you already gave X into that thread. You can't play with it afterwards. That's going to cause bugs. So Rust can actually statically determine that you do not have memory erase conditions, which is right? I've read books about how to program defensively to avoid this problem, and now the compiler just does it for me. So that's amazing. And it gives you this great error message. I mean, relatively great. I don't know. I think they're great now, maybe not when you first look at it. But basically it says, hey, note, X moved into the closure here because it has the type send, and you can't use it after you've moved it around. It also complains because X is immutable, and we tried to add 1 to it, which was what the question was, basically. So there's two problems with this code, and Rust is able to tell you at compile time that both of them are a problem and will not let you actually compile your program. So that's super rad. Also, the other great thing about Rust, and something that I consider to be a basic feature of modern languages, which is not always true, but I think should be true, is that Rust does not actually have null. So it's impossible to use uninitialized values. You can't have null everywhere. You're not like nil checking all the things. Back in the day with Rails, that used to be the bug everyone would get right, is that like unidentified method whatever on nil, ID 4, right? And you see those all over the place. That's like not possible in Rust at all. And we'll talk about how to handle that. I believe on the next slide there is a way to sort of do it, but much more safely. Yeah, so check it out. If you've ever used a language like OCaml or Haskell, you may have heard of like option types. And so what Rust does, it does not have null, but it does have an option type. So what an option type does is an option type says it's like a type on a type almost. So the option type will say you can either have a value or no value at all. And what's interesting about this, it sounds like nil, but it's different in the reason that because the types are different, Rust will not allow you to, say, do operations on a null value because it has a different type than the integer. So say we might return an integer from a computation and we might not. So we would say, like, call a function and give me x back, x, add 1 to x. If we didn't handle that option, it would say, wait a minute, you're trying to add 1 to an option int. You can only add 1 to an int. So compile time error, not actually true. So this is the example with strings. So we have a function here that returns a boxed string. And the capital B box, the brackets, is how you write the type of what box the lowercase thing returns. So we could return a box string, or we could return an option box string. And in this case, we have to say sum box a box string, because the two values for option are sum and none. So sum means I have a value, none means I have no value whatsoever. And because of Rust type system, and what I told you earlier about match statements and the fact that they force you to handle every case, means that if something returns an optional value, the compiler actually forces you to handle the null case. So this means that you don't get the same class of errors about forgetting that something might be nil, right? Have you ever had a problem in Ruby where you get that nil error, but the actual problem happened 4 functions ago, right? Because you didn't realize you were passing nil through a ton of things. It's not possible in Rust. And so what Rust lets you do is it lets you match on the values. So message is a function that returns an option box string. And then we match against the message and we say, hey, if we have a sum string, we print it out. If we have nothing, in this case, we just don't do anything. But you could handle the error in whatever way that you wanted. So that's sort of the way that Rust tackles the problem of nil. And it's generally considered to be the right way to do it by most people now. If you didn't know, the guy who invented nil's name, I believe, is Tony Hoare, I think. And he did a presentation where he basically said, he calls it my $1 billion mistake. He regrets inventing the idea of nil. Because it's caused so many problems and errors and things. So yeah. So here's another interesting thing about Rust. It doesn't really support object-oriented programming, but it supports something that kind of looks and feels like it. So in this case, we have a struct called timebomb, and it has a value called explosivity that's an unsigned integer. So if you use C or C++, a struct is kind of like a collection of values. You have 5 or 6 things. And so this is laid out the same way as in C as well. But instead of say, so in Ruby, we would say this would be class timebomb adder accessible adder accessor explosivity, right? And then we define a method in that class. In Rust, we instead have structs which just have our data and traits which just have our methods. And you can implement a trait on a struct, and you get something that kind of feels like an object, but it's not quite exactly. So Rust calls destructors drop. So what happens with the timebomb struct is whenever it gets deallocated, it calls this drop function, and basically it says for the number in the range of 0 to the explosivity, it prints blam. So if you have a time bomb with 5, it goes blam, 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 blam. If you have one with 10, it does it 10 times or whatever. And so this is how you actually define a trait. So traits sort of vaguely look like interfaces. They're actually more close to type classes in Haskell than they are to interfaces in Java. If that means anything to you. If it doesn't, don't worry about it. But basically, so here's another trait we call printable. And we say the printable trait means that you have a function print. And it takes self because if you've ever programmed in Python, Ruby sort of implicitly sets self for you. Languages that prefer to be more explicit kind of force you to pass self into the function. But so we implement printable for the time bomb, and we say, okay, the implementation of printable is for function print at self, so it's got the same type signature that it had in the trait. We print ln, my counter is, and then what the value of explosivity is. So you can inspect what a time bomb is. And then we make x be a time bomb with an explicivity of 5, and then we call x.print. And you need the parentheses every time. You don't need them in Ruby, but you do need them in Rust. And what this actually does is, this actually turns into, it looks like OOP dynamic dispatch stuff, but this is actually statically dispatched to that print function. Again, if that means anything to you, if it doesn't, so don't worry about it. This is always the balance of like the people who do low-level stuff already and don't. Yeah, but so what happens here? Oh, I wrote a lowercase t. That should be a capital T. There is a typo on my slide. I apologize. So what's interesting about traits is we can write generics over a value. So this says a function print all for a value t. That should be a capital T. I'm sorry. And it takes an array, a vector of t's of printable things. And then for everything, it prints that out. Right? So it just calls print on all of them. The problem is this will actually fail to compile. And the reason it will fail to compile is that Rust will say, hey, you just said t. A t could be any type. Most types don't implement printable, so this would not actually work, right? If I passed an integer into this function, it would not have printable defined on it, so it would fail. So Rust fails at compile time and says, hey, you can't just use t's. So what will work is if you say, oh, you know, I bet this is HTML screwing up. I bet I missed an ampersand. This is also another typo, apparently. So print all where t colon capital P printable without the equals and quotes. HTML, man. The less than and greater than signs, I have to like copy and paste the code in and then like manually replace them with amp GT. Apparently I missed this one, so sorry about that. I didn't notice it when I looked over my slides. But you say t colon capital P printable, and that says, hey, I want to type t. I don't care what type it is, but it has to implement this trait. And because we know it implements the printable trait, we know that it has the print method, and so we know that it can actually call printable on the or print on the thing, and then it just works. So that's sort of like generics and then bounding generics by traits. Yeah. Now what's fun about it is you can actually do traits on any type, including basic types. So this is very similar to Ruby in that, you know, I could actually implement printable for int and then just print out the number and then call 5.print, and this will work. So this is very similar to Ruby, and this reminds me of all the ridiculous Ruby things. And as it turns out, Yehuda actually ported a little bit of active support to Rust, with the caveat of we should never, ever use this code for anything real, but just to demonstrate that it's possible. So time equals time now, and then println time. The question mark identifier basically says use reflection to figure out how to print out this thing. So we can actually do 2.days.from now, and 2.weeks from now, and 2 months from now, and 2 years from now, and this will all work. Now, the reason this is a little more sane than Ruby is that you see these use statements. So extern mod says it's like require in Ruby. So like I want to use this external module. And then you have to say, I want to use active support period and active support time. And so these like monkey patches are only valid in the scope where you use these traits. So if I had another library that used integers, they would not have these values on them. Whereas in Ruby, they're globally, you know, and that's like the issue and why I went through this whole refinements debate. This is actually only valid in the scope, so it's a little better than in Ruby. We still don't want to encourage doing this. Nobody is like building this for Rust and saying we should do it this way. It was just solely as an experiment to like compare. And this is one of the reasons why I think that Rust might be useful to Rubyists is because we can build things that feel like our Ruby code, but have a lot more checks and are a lot faster and like take advantage of all the static stuff. How much more time do I got? Is it 10? Is that the right number? Cool. Okay. So those are all the code samples I want to show you. There's a bunch of stuff I didn't show you because I only have so much time, but I'm going to talk to you about production. So Rust is not yet at 1.0, which means that things are still in a bit of flux. We are going to hit 1.0 this year, though, and there are currently 3 people using Rust in production that we know of. So you could be number 4. But those 3 production deployments are really, really valuable for learning things about the code. Basically, I always forget the second one. The first one ever was OpenDNS was using it for like routing stuff. So they were like running it to route requests to different servers and things like that. The second one, totally forgot. I never remember. The third one is Yehuda and tilde. So this is another reason why I think this is interesting to Rubyists is, Yehuda and tilde are making this product because every consulting company realizes consulting sucks and moves to products eventually. Tilde is building this product called Skylight, and Skylight is basically New Relic but way more baller and just for Rails apps. So they originally wrote the collector agent in Ruby until they realized that added a whole bunch of overhead. The memory usage was all over the place. They tried then implementing it in C, and they still got memory leaks. And when you ask someone to install a monitoring tool on your computer, you had better not add a memory leak to their production server, right? It's kind of rude. And so they actually ended up rewriting the collection tool in Rust. And so if you use Skylight today and you gem install Skylight, you will get a gem that's implemented in Rust. So that's the third production deployment. And because of the memory control, they were able to basically use almost no memory, and they were able to make sure that they weren't leaking memory anywhere. And so it was super, super advantageous for them to use it. And so that's why they're doing that stuff. And that's another example, I guess, is that literally Rails apps are going to be running Rust code. So that's why I think it's relevant to Rubyists as well. So Rust is pre 1.0. It's stable-ish. So for a while, there was not a whole lot of changes, and in the past month, there was 3 breaking syntax changes. The reason I say ish is because all 3 of those changes, while they were syntax changes, they were you could write a very tiny Ruby script that would use regular expressions to fix your code. They were very minor and easy to fix. It was instead of doing this, do that. So it's not like things went away. The other thing that makes it stable-ish is that the standard library is still undergoing development, and so those interfaces are changing and stuff. But they're actually starting to become stable now, and it's every single release of Rust that comes out, there have been less and less and less changes that break stuff. So it took me, I wrote this book called Rust for Rubyists on Rust. It's about a 50-page book. It uses some of the basic features of the language. It took me 2 hours to update the 50-pager to the next version of Rust, the last one. The previous one took me a day. The one before that took 2 days. So it's been getting less and less and less. But once it's going to be following Semver very strictly, so once 1.0 actually happens, the code will be good for 10 years. So there's a whole large community of people that have been very interested in using Rust that basically are as soon as this stuff's 1.0, man, and I've got to keep relearning new things, I'm using this all the time. So we're going to sort of see an explosion of usage after 1.0. But one of the other cool things is that communicating what stability actually means will actually be marking, you will have to opt into unstable features. So for example, one of the things I did not talk about is macros. So instead of C++ templates or C preprocessor substitutions, Rust actually gives you Lisp-style macros where you operate on the AST of the thing that you are doing. And they're super amazing and wonderful, but the implementation might change, so you have to opt into the feature and say, I know I'm using something really unstable, and so I promise not to get mad at you later when you break my code. So we have sort of static checks. You can guarantee that once 1.0 happens, you can know that you're only using stable features and that you're not going to have to update your code later. I don't want to have to go through the Ruby 1.8 to 1.9 transition ever again in my professional life if I don't have to, right? And 1.0 will be happening this year. So hopefully in the very near future, I'll be able to give you a fully stable Rust that you'll be able to use for a decade. That is the wrong button. So in my last couple minutes, where can you learn more about Rust? Because this is only a very short talk. There are 3 introductions that exist. The first one is the official tutorial, and it's terrible. The second one is the thing that I wrote called Rust for Rubyists, which, while I am obviously biased, other people say it's better than the tutorial, so take their word for it, not mine. And the last one is relatively new and is really great, called Rust by Example. And so it sort of shows you feature by feature what the syntax looks like and all those other things. The official tutorial will get better very soon, but it's sort of been patched together by a bunch of people over a very long time, and so it's not very good at the moment, but we'll fix it. There's also a bunch of discussion forums. There's a Rust dev mailing list. I hate Reddit, but the Rust subreddit is really amazing and wonderful, so I have a Reddit account basically mostly just for that, although I've started reading other Reddits again because Reddit. But it's really great. There is a Pound Rust on the Mozilla IRC room, and they are wonderful and amazing. And I don't say that just because I'm in there too, but you can ask the most noob of questions, and they will not call you stupid. I went in there a month or 2 ago because the print function had changed. There was something about importing that was different, and I literally joined in and was hey guys, I know I've been working on Rust for a year now, but how do I print a string again? And they just said, oh, it's this, instead of being like, are you serious? So it's super wonderful and communicative. You can ask whatever question, and they will be happy to expand at length as to what the details are. There's also a blog that happens called This Week in Rust that one of the contributors writes. And so it covers what has happened in the past week and all the breaking changes and new features and all the kind of stuff that's happening. And so it's a great way to learn about what's going on. You can look at all the code at github.com/mozilla/rust. And with that, I am out of time. So I want to say once again, thank you so much for having me here. Thank you for showing up this morning.